In this podcast, we will introduce the cardiovascular system, focusing particularly on the electric activation of the heart. The heart is the organ which pumps blood through the blood vessels of the body. The cardiac comes from the ancient Greek word meaning heart, and so cardiology literally means the study of the heart. Invertebrate heart is principally composed by 4 chambers. It's an organ which is made mainly with cardiac muscles, which is very peculiar because it's an involuntary muscles, although it is striated, so it has the same anatomical composition as the voluntary muscles, which normally are stronger than the involuntary one, which means that it's an involuntary muscles, but it's fairly strong. In the average human being, the heart beats 70 times per minute with approximately 2.5 billion times beats, 2.5 million beats over the average life of 66 years lifespan. And it pumps approximately 5 liters of blood per minute. Its weight is normally between 250 and 350 grams, and we normally say that the heart is more or less as big as your own closed heart. For this podcast, I assume a fundamental knowledge of the heart anatomy, which I have added some free podcasts that you can find in internet, which will give you a fairly good understanding of fundamental underlying concept of anatomy for several organs, in this case particularly for the heart. So my recommendation is that you take some time to look at least this podcast, and then there will be other during this webinar which will contain further deepening, which again you can find in internet. I've checked before recording this lecture that they are still there and freely available for you. Now, as a very quick summary, our heart is made of 4 chambers, the 2 upper ones which are called atria and the 2 lower ones which are called ventricula. The human heart has a septum into the middle, which is the wall of muscles which splits completely in 2 parts the heart. So the 2 ventricula in normal condition, they do not communicate among themselves, and the same for the 2 atria. So the upper ones are the atria, there is no direct communication of blood among the atria, and the 2 ventricula, once again, there is no blood communication in normal condition among the 2 chamber, the 2 ventricula. So the heart the blood enters the right atria, it gets down to the right ventricle, through which it gets up to what we call the small circulation. So it goes to the lungs, and then it comes back, it enters the left atria, from the left atria goes into the left ventricles, and from these, through the aorta, it goes through what we normally define as the great circulation. Blood is pumped from the left ventricles to the heart and the capillaries into the periphery of the blood through the arterial vessels. This is called great circulation or systemic circulation. And then it returns through the vein to the right atria. We normally assume that we are looking at the human being, which is at the same position as the slide. Therefore, this would be the right side of a man which is looking at me. This is what we call the anatomic position. So I will refer to the right to this side and left to that side. So it returns via the veins, vena cava superiore, vena cava inferiore, filling the right atria and then again pumping the blood to the ventricle. But we will come back on this in detail in a few slides. We define the cardiac output as the amount of blood that the heart is capable to pump, and it is calculated as the heart rate in 1 minute. Therefore, in this slide I put about 70 beats per minute, times the amount of blood that the heart is capable to pump out for each contraction, which is about 0.08 liters. Therefore, in 1 minute, and that's what defines the cardiac output, we assume the average man to be able to pump something like 5.6 liters per minute. And now, if this is the amount of blood, this is the cardiac output over a minute when you are in resting condition with 70 beats per minute, you can understand that if I move from 70 beats to something like 140 beats, then the cardiac output can be doubled. No, that's the way in which the heart reacts if I start running, and there is a need for more blood towards the systemic circulation. So I increase the heartbeat. Because of that, I can double or even more my cardiac output for brief periods, obviously. Now, let's dig down into the electrical activity which controls the heart contraction. We will see in this animation that all starts from a very specific point of the atria that we call the sinoatrial node. And then the stimulus propagates through the walls, to the muscles of the atria, and it arrives to the so-called valve plane. So those are the two chambers, atria, that I was mentioning before, and those are the true ventricula that I was mentioning before. Therefore, the heart is made of 4 chambers, 2 atria and 2 ventricula. There is no direct blood communication among the atria, nor among the ventricula, but each atria pumps blood to its own ventricula, and from the ventricula the blood is pumped out through those veins, actually arteries. And then among the atria and ventricula we have the so-called plane of valves. In fact, all the valves, those dividing atria from ventricula and those dividing ventricula from the arteria, are placed more or less on this plane. So the contraction, the electrical activity triggering the contraction started from the sinoatrial node, which is a pool, a node of cells which are highly specialized, and electrically speaking they behave more like neuron cells than as muscle cells. Once again, in those podcasts you will find definitions of electric activity of neuron cells and muscle cells, which they are slightly different. And then it propagates through the muscles cells through both atria. When the stimulus arrives to the valve plane, it cannot propagate because the valve plane is not highly conductive. There is only one point which is conductive, which is the so-called atrioventricular node, which, as well as the sinoatrial node, is made of specialized cells which can be highly conductive, and as the atrioventricular one and as the sinoatrial one, they have a peculiar property, which means that they can self-excite themselves. So even without getting any external stimulus, they will contract, they will trigger the contraction. And then once the stimulus, therefore, has started from here, propagated through the atria muscles, arrived to the plant, there is only one point which can read the stimulus as if it was an antenna. This means that the stimulus enters the atrioventricular nodes, and this passes through those represented as yellow channels, which we call atrioventricular bundles. It arrives through the interventricular septum to 2 branches that we call right and left bundle branches, through which they arrive to the apical part of the ventricula, entering the so-called Purkinje fibers, which are innervations of the ventricular muscles, and through there they are released to the wall of the ventricula. And in this animation you see now the contraction, the systole of the atria, which triggers the systole of the ventricular. So the heartbeat is actually made of different phases, and we'll see this in a second, but we can now identify already 3 different phases. Atria contraction, also known as atrial systole. After a while, ventricular contraction, also known as ventricular systole, and those two together are known as heart systole. So atrial, ventricular, and then relaxation, starting from the atrium and then the ventricular. But I will come back on this concept once again. Let me repeat with another animation how the contraction propagates through the heart, and in these slides you will find the description associated with the animation. So the contraction starts in the sinoatrial nodes in the right atria. Remember, this is as if I'm looking specularly, well, not specularly, but to a man which is facing to me. Therefore, this would be the right side of his heart, and this would be the left side. And now, from the contraction starts from the sinoatrial nodes, those very peculiar cells which are in this part of the heart, and then propagates in all the right atria, and then from the right atria to the left atria, as you have seen in this animation. And through that, they arrive to the so-called, as I mentioned before, valve plane, which is not conductive, therefore the propagation cannot continue across these valves, apart from this plan of valves, apart from one very point, which means that now the stimulus is entering the atrioventricular nodes, from which it arrives to the atrioventricular bundle branches, which split into left and right branches, arriving to the very apical part of the ventricula, through which this electrical signal is released to the muscles of the ventricula through those indentations which are known as Purkinje fibers, which actually release the stimulus to the muscles, starting from the apical part and then getting up to the ventricular walls. This is very significant because, and this is the end of the animation, but this is very significant because this synchronism is crucial in order to maintain the heart in a very good functioning, as we will mention in a while. But we have seen now that everything starts from this sinoatrial node, propagates the signal through the atria muscles, and now that the electric signal is arrived over there, the atria will contract. While the atria are contracting, the signal enter the atrioventricular node, and through those bundles arrive to the apical part of the ventricula, which are therefore the first contractive, and then the contraction propagates together with the electric signal towards the upper part of the ventricle. Therefore, the contraction upper from the upper part of the atria towards the bottom part of the atria, and then from the apical part, the bottom part of the ventricula, towards the apical part, the upper part of the ventricula themselves. Therefore, this contraction is made in a way that it maximizes the ejection of blood. So if the contraction is starting from the apical part of the ventricle, this means that this contraction is not closing, is not creating turbulence towards the blood which is flowing through the valves which separates the atria from the ventricle. If it starts from the bottom to the down, then this is, from the top to the down, this is maximizing also the ejection of blood. And the same, and this is even more important, has to happen in the ventricula. The contraction starts from the apical part of the ventricula, the bottom part, and then propagates towards the upper part. This is important because the only exit is up. Therefore, if the contraction would start above, it would occlude the way of the blood, creating turbulences. And turbulences in the blood are never good because they can create small coagulus, which therefore will give up severe consequences such as ictus or stroke. So this synchronism in the contraction is really important. In the ventricula from the top to the bottom, and in the atria from the bottom to the top. And this is the best possible way, or this is the way our heart evolved, in order to maximize the ejection of blood through the valves. I think I described this here, so this timing is crucial to avoid arrhythmias, which is one of the consequences. In fact, the atrial muscles with respect to the ventricular muscles are activated earlier. Atrial contraction starts first. They enter in a period which is called the refractory period valves, which means that they cannot be excited for a period of time. Therefore, the ventricular contraction cannot send the signal back to the atria. So the atria can trigger the ventricular cannot trigger the atria. And that's because after contracting, the heart muscles, the atria in this case, have a period which is called refractory phase, in which cannot be excited again. And now the stimulus arrives to the apical part of the ventricle, which contracts, and now they are entering the refractory phase. So the upper part of the ventricle cannot excite the lower part of the ventricle, because if this would happen, this would create atrial or ventricular fibrillation, generating severe problems into the synchronic mechanism of the heart, which, as I mentioned before, is what really make the cardiac output maximized, no? Because there is no turbulences in this very well organized beat, and the amount of blood that the heart can inject to each heartbeat, it's maximized, and it's in the amount that I mentioned before. Now, let's try to dig it down. In other podcasts that I have introduced as a link in this presentation, or given you before for other in the as podcasts, introductory podcasts to anatomy and physiology, you can dig out the electric activity at cell level. And if you look at how this evolves, assuming you could measure the voltage across cell membrane of the cells in those different points. So if I would put here an oscilloscope with one probe within a cell and the other probe outside the cell, this is how I would see the change of voltage. This voltage would start being negative, and then when this is triggered, the voltage would get up, arriving to values which are in the order of few tens of millivolts, and then it would stay in this state for a short period. The scale here is that each of those grid is representative of 0.1 seconds, so it stays up to there for about 150 milliseconds therefore, and then it gets down to the previous value. And then again, this is a cell which can repolarize itself, therefore naturally the slope of this cell is not zero, but it is getting out again, and once it reaches a given threshold, it shuts, and then it repeats this profile over time. But now, if I move my oscilloscope to cells which are in the atria muscles, I could see that over time the potential would have a different shape. First of all, this is flat until a stimulus arrives. So differently from the sinoatrial node, the atrial muscles cells, they cannot self-excite. So they have to wait for a trigger in order to be excited. And once this trigger arrives, the voltage moves from minus 20 towards something which is plus 40-50 millivolts. And then we start observing here a plateau, which was not present over there. So the voltage will stay in this value for a while. In the atria, it's about something like 100 millivolts. It stays there, and then it gets down. And this is when we are in the so-called refractory phase, because the cell is depolarized and cannot depolarize more. This plateau is crucial because this means that this potential lasts longer than the one we have seen in the sinoatrial node, allowing the sinoatrial node to repolarize before the atrial muscles have repolarized themselves. And that's what really triggered this synchronism. The fact that the sinoatrial nodes are the first to get contracted, but also the first, to get excited, but also the first to get back to the original value of voltage, while the muscles of the atria have this plateau. And now if you get down in this diagram, we observe that this plateau is growing as far as we get down into the heart, with one exception, which are the atrioventricular nodes. The atrioventricular nodes, they have a behavior which is similar from the electric point of view to the sinoatrial nodes. It's just that this is larger. Why it is like that? Because the atrioventricular nodes can also self-excite themselves, but they are much slower than the sinoatrial nodes. And this is a mechanism of the heart in order to protect from blockages. So in case the sinoatrial node does not depolarize, does not give the pace to the heart. There is a spontaneous depolarization from the atrioventricular nodes, which is much slower, in the order of 50 heartbeats per minute, but it's still enough in order to keep a human being alive, probably unconscious, but alive. So this is a double engine, a double trigger, a double pacemaker, which is a security mechanism in order to ensure that even if the first one fails, the second one can still trigger the heart. But it has to be slower, in order to give to the sinoatrial node the time to do its own job and trigger the atrioventricular node and the other cells. And then from the atrioventricular node, the stimulus gets down to the ventricular myocardium, where it is released to the muscles. And those are muscles, therefore they have the plateau. And in this case, the plateau is larger than the one we have seen in the atrial muscles, in the atrial myocardium. And the fact that there is a plateau, and this plateau is larger towards the base of the heart, this is what really guarantee minimize the number of arrhythmia within the heart. I think I have also an animation here, so everything starts from the sinoatrial nodes, then it propagates to both atrial chambers, it arrives to the valve plane, which is not conductive, apart from the atrioventricular node, which acts as a sort of antenna. And now from the atrial muscles, this is the way it behaves electrically, each and every cells. There is a plateau. Because of this plateau, there is no propagation backward, no? And now this propagation arrives to the atrioventricular node, which as commented below, as you can see, there is a tendency to get up without anything, which you don't see in the muscles of the heart. So the muscles, they cannot self-repolarize. The cells of both atria and the bundles, it can, but much slower, waiting for the above one to trigger themselves. If this trigger doesn't arrive, they give the pace to the heart. And so getting down, you see the diagram that we discussed before, till we arrive to the very tip of the heart, the Purkinje fibers, where the stimulus is released to the muscles, which behave like that. So they have an excitation moment, and then there is a plateau, and then there is this repolarization. Let's go back on a very schematic representation of the heart. Right atria, left atria, the sinoatrial nodes, atrioventricular nodes, and the bundles terminating in the Purkinje bundles. Right atria, right ventricular, left atria, left ventricular. Everything starts here, then it propagates, it arrives to the valves, which are not to the plan of valves. It can be read only from the atrioventricular nodes, propagated through the bundles, and from the bundles from the apical part of the ventricular to the top part of the ventricular. If I put again the ECG over there, then from this animation you should understand that the stimulus propagation from the from the sinoatrial nodes to the valves through the atria is actually what gives us this P wave, because this propagation is simultaneously triggering the atria contraction. And then the stimulus gets down, there is a contraction of the ventricular, which is what gives us the QRS complex. And then again, the repolarization of the ventricular is what really gives us the T wave. This diagram is really important, and this we have to pay particular attention. This is reporting the pressure in millimeter of mercury over times scaled in terms of hundreds of milliseconds for each square. And there are three values over there. The left atrium blood pressure, the left ventricular in red blood pressure, and the blood pressure you measure into the aorta. Now, if we start from down here, we see that the left atrium blood pressure is higher than the one in the left ventricle. This means that we are in the atria systole stage. So the contraction of the atria, that's when the blood pressure into the atria reaches its maximum, which, by the way, it's comparable with the blood pressure you could measure in the local circulation of blood, the peripheral circulation of blood, which is in the order of 20-25 millimeters of mercury. But at some point, the systole is completed. Systole means that the atrial contraction is completely filling the ventricular with blood. And now that the ventricular is completely filled with blood, there is an increase of blood pressure within the ventricular, which in fact in this point overcomes the value of the atrium. And if the left ventricle blood pressure increased the one of the left atrium, this means also that the valves separating the atrium from the ventricle is now closed, because what really activate, close and open the heart valves is actually the difference of pressure from one chamber to the other. They're not active valves, they are passive valves. So while the atria is in systole, which means the blood pressure is higher than the one in the ventricle, the valves conducting blood from the atria to the ventricle, the so-called atrioventricular valve, remains open. And now there is a moment in which this valve is closed, but also the valve which links the ventricular to the atria, the so-called aortic valve, to the aorta, which is the main blood cells getting out from the left ventricle, which brings the blood to the systemic circulation. This is also closed. So in this moment, both valves are closed. The ventricle is completely isolated, and the contraction is started. So the blood cannot go anywhere else. The blood is a fluid, therefore is not compressible. Therefore, there is only one thing which may happen. The blood pressure is increasing. And the more it increases, the more the contraction insists, the blood pressure is increasing, and it arrives to the point in which it overcomes the blood pressure into the aorta. When this happens, then obviously the valve separating the ventricle, the left ventricle, from the aortic vessels get opened. Because now the pressure into the aorta, into the ventricle, is higher than the one into the aorta. And once again, that's what really triggers the valves. So we moved from the isovolumetric contraction. So here I don't have change in volume because the fluid cannot be compressed. Ideally, there is a small compression because the blood contains gases, but as a fluid, you cannot compress any fluid. So to a contraction, the only reaction the fluid may have is to increase the pressure. When this pressure overcomes the ones into the aorta, it's starting the so-called ventricular ejection. So we are ejecting blood into the systemic circulation through the aorta. And this will keep going. Is actually a fast ejection, which is when the blood pressure arrives to the maximum, and then a slow ejection, which is from this part of the diagram when the blood pressure is getting down, but still we have the value of pressure in the left ventricle, which is higher than the one you may measure in the aorta. This will at some point change, because once this value gets below 110 millimeters of mercury, now this is another crucial point, because the aortic valve closes again. So we are here, and now the contraction, the systole of the ventricles is ended, so there is nothing pushing, so there is a drop down in pressure. This is again a nice volumetric drop down, because the ventricle is completely void now and cannot diminish its volume. So this blood pressure gets slightly down, and it will reach again the value of about 20-25 millimeters of mercury, which means now it will get below the blood pressure value into the valve, into the atria. And this is what will trigger again the opening of the atrioventricular valves, which therefore will open, letting the blood flow again from the atria through the ventricular. So atria and ventricular, they start recharging, refilling with blood during the diastole. This is pushed down with the systole from the atria to the ventricular, and the systole of the ventricular will start before the aortic valve is open, which means that there is a stage in which we can only increase the pressure without releasing the blood. But when the blood pressure will overcome the one in the aorta, then this will open the valve and the blood will flow out towards the systemic circulation. This is what we call heart cycles, or the cycle of heart contraction. So there are three things which you need to pay attention to. The electric activity as signal propagation towards the heart, as I commented in the previous slides. This is actually affecting the contraction of the muscles, which therefore are transferring pressure to the blood, which is within the atria or the ventricular or now into the aorta. And this will trigger the opening or the closure of the four of the valves that I commented before, two valves. And this will give the 6 different phases of the heartbeat, as you can find them in this graphical representation. I took this from a podcast, which is an open repository, Wikipedia, for human physiology, which I find very interesting. At same level, this is peer-reviewed work, so it's as good as many books I could suggest you, but this is over the web, so you can reach it easier. And I also put again links to animations, cartoons, which explains this mechanism in a very clear manner. So I think using cartoons for explaining physiology, it's a very good approach, cartoons, animations. Okay, now, because we are engineers, we can represent this mechanism using a Carnot cycle. So if we represent the volume and the pressure of the left ventricular within the left ventricular during systole and dystole, we can draw a Carnot cycle. The Carnot cycle is probably something that you have studied in many other branches of engineering. And let's comment this Carnot cycle. Let's imagine we start from A. A means that all valves are now closed. All valves means the ventricular has 2 valves, one to filling, the atrioventricular valves, and one for the ejection, which is the ventricular, the atrioventricular valves. We are in the left ventricular. And now, all valves are closed, the contraction has started, we are now in the systole, in the ventricular systole, but blood cannot go anywhere else, because the blood cannot be compressed, or not that much. If there is a small compression, is due to the gases which are within the blood, for instance the oxygen, and it goes up till a point B, which is when the aortic valve opens. And because of the previous slide, now you know why this open. It's the point in which the blood pressure from the ventricular overcomes the value of the blood pressure into the atria. This will trigger the opening of the atrioventricular valves, and therefore the ejection of blood from the ventricular to the atria, towards the aorta, in direction of the systemic circulation. This is the fast ejection and then the slow ejection, and then we reach the point C. Point C, again, all the valves are closed. All the valves are closed. The pressure, the volume is at the minimum possible, about 50 milliliters, and this is the empty ventricular. If this is emptied and cannot become smaller than that, there is now a drop of pressure, and this pressure will get down and down and down till its values will get below the pressure we have measured into the atria, point D. If this value gets lower in the ventricular than in the atria, this will trigger the opening of the so-called mitral valve, which is the valve dividing the atria from the ventricular. The left, it's called the mitral because it has this shape which reminds the mitral hat, which is the one which the Pope wears in Rome. So this is another way to represent the cardiac cycles. It is very clear for an engineer because this is using the Carnot cycle. And now, if you know what it is, the meaning of the Carnot cycle, you know that the area below the curve BC is giving you actually the work that the heart as a pump offer in order to eject the blood, while the area below the curve DA is giving you the work which is required in order to fill again the ventricular. So this is the Carnot cycle of the ventricular. So the upper curve, the area below the upper curve, is giving you the energy and what is proportional, the energy and the work that the ventricular would do if we measure using a Carnot cycle. It's the energy released towards the systemic circulation, while the one below is the one required in order to fill again this pump. The difference among those two areas are giving now the efficiency of this pump. And as you can see from this diagram, this is a very efficient pump. Actually, it is about the 90% of the wall energy which we transmit from the ventricular to the systemic circulation. Less than 10% is required in order to refill the ventricular. So overall, it's a very efficient machine. And now I think it's really interesting to look at the Carnot cycle of the ventricular together with the same diagram that I used before, and put this in relation with the different value of the pressure within the atria, ventricula, and aorta. So I mentioned that this is over time. At some point, which is when the systole terminates, the blood pressure value within the left ventricular becomes higher than the one into the left atrium. And this is what really triggers the point A, this point. So now the atrioventricular valve is closed and also the aortic valve is closed. So for about 20 milliseconds we get both valves closed. If both valves are closed and the ventricular is in systole, is contracting, this means that there is only one thing you can observe in this chamber, which is a sudden increase of pressure, as you see here, between the point A and point B. Point B, now the value of blood pressure within the atria is overcoming the one within the aorta, therefore the aortic valve is now opening. And if this opens, we may have the ejection of blood from the valve, from the ventricular to the aorta. There is a fast ejection and a slow ejection, and then we arrive to point C. Point C is when the systole of the ventricle is terminated, the valves are closed, the two valves are closed, as you can see from this animation, mainly the aortic valve, because the value of the blood pressure in the ventricular becomes again smaller than the one in the aorta, and the atrioventricular one because it was closed also before, because the value is much higher than 20-25 millimeters of mercury, as you can read from this diagram. Those are now in scale, more or less. And this is when both chambers are in diastole. So it's not correct to talk about systole and diastole for the heart as a whole, but there are several phases, 6 as I mentioned before, which are all in this diagram. So the systole of the atria will trigger the systole of the ventricula. There will be a switch in volume in pressure from the atrium ventricular, and this will trigger the opening or closure of the atrioventricular valves. This will replicate towards the atrium. So this is when we have the systole with fast ejection and slow ejection, and then both chambers are in diastole. And that's where both chambers, there is a first phase in which only the atria can fill, because the atrioventricular valves are still closed. And then there is the second part of the diastole, when the atrioventricular valve is open, the aortic valve is closed, so there is nothing else which can happen than the atria refilling. And this is the stage D. And this is stage D when the blood pressure gets still down, because now the muscles walls of the ventricular are completely relaxed, they offer no resistance, and so they can refill and open, and they reduce further the blood pressure. And then there is still a phase of refilling in which the pressure slightly starts growing, but slowly, till again we go back, because this is a cycle, to the point A. So now both chambers are closed, the ventricles are contracting, we are in systole, and because we are in systole, the blood pressure rises up again, and the cycle will restart. Though this is a very efficient cycle, if you measure the Carnot cycle, you find a huge gaining in terms of energy that we can give to the systemic circulation versus the energy we need in order to trigger, to refill the ventricles. And putting together those two diagrams, you can really understand the triggering due to the electrical activity, systole and diastole, contraction of the muscles, and transmission of pressure to the blood within those two chambers. Now, once this happens, therefore, we are ejecting the blood to the aorta, and from the aorta, this splits into parts, feeding the brain, which is actually using a huge amount of blood and particularly oxygen in the blood, and then also in all the other systemic circulation. So this is blood which is moving from the heart to all the organs. Is red in this animation, suggesting that this is full of oxygen because it's coming from the pulmonary circulation. Now it releases the oxygen to all the organs. It becomes blue, which means poor of oxygen in this animation, and that's also true if you get a drop of blood from the aortic circulation. This is very red, and this color is given from the oxygen. If you get blood coming out from the veins, this is less red, more towards the blue, and this is because now there is no anymore oxygen. And now from these organs all the blood is collected, and through the vena cava superiore if it comes from the brain, and vena cava inferiore if it is coming from the systemic circulation, the blood is back to the atria. From the right atria moves to the left ventricle, because now the valve are open and you know now why, and then from the left ventricle it gets pumped up to the lungs, and through the lungs it gets refilled of oxygen. And now this becomes again red in our animation. Go back to the left atrial chamber, where all the cycles will restart again and again up to about 2.5 million of time during our lifespan. There should be a last animation, if I remember well. This is the same but much faster now. This is the animation I was mentioning. So the blood arrives through the systemic circulation to the very periphery, where it releases O2 oxygen, get on board CO2, and it changes color. This is true, it really changes color. And now from the other side it arrives to the lung, and here we have a similar animation, but here the mechanism is the opposite one. So the blood arrives to the lungs, where it releases CO2 and accumulates O2, which is binded to the red cells. And now the cycles can restart.